Hello. Hello. We'll be starting in a couple of minutes. Yeah. Good afternoon, everyone. I'm Ritvik, and Paris and I will be conducting this session on exoplanet detection. Yeah, we want this session to be as interactive as possible, so feel free to ask any questions along the way if you have any doubts. One second. Uh, yeah, can you guys see my screen? Okay, I'll stop presenting. So basically, this talk is going to go over all the different techniques that are used to find and characterize exoplanets, and we'll discuss their advantages and their limitations and so on. Exoplanet detection as a field is relatively new in astronomy. So you might have read in the module before the 1990s, there were no confirmed exoplanets outside the solar system, and until even 10 or 15 years ago, there were only about 1,000. And today there are over 6,000. So, this whole field of exoplanet detection is barely 30 years old, and there's a lot of stuff evolving even today. So, first of all, before we begin, these exoplanets don't really get seen directly most of the time. They're almost always inferred from sort of small side effects on brightness, position of the star, things like that. So, all the methods that we discussed today will just be different ways of asking what changed because there was a planet going around the star. So first up, what is an exoplanet? An exoplanet is basically just a planet outside our solar system. So famously, the IAU, they define a planet as being a body that is in orbit around the sun, has sufficient mass to achieve hydrostatic equilibrium, which is just a round shape, and it has cleared the neighborhood around its orbit. So by this definition, there are 8 planets in the solar system. And for exoplanets in general, we will be extending that first criterion to objects orbiting stars other than our sun. This is still some kind of a loose definition because there's also rogue planets that don't orbit any star. So this is kind of a messy category, but practically for detection, we're going to use the same definition and assume that these are planets orbiting other stars. So the first question is, why should we care about exoplanets, right? Why do they matter to astronomers? All of the exoplanets that we find are sort of basically test cases for our theories of how planets form and how solar systems form and behave, right? So it basically tests our theories of physics and astronomy, and it helps us learn more about our own solar system as well. We've now found thousands of systems, which basically let us classify all these different kinds of planets, right? So we find Earth-like planets, we find what we call hot Jupiters, cold gas giants, and so on. And this allows us to form a much richer picture of the universe than we would be able to if we were just trying to generalize from our solar system. If you, for example, if you look on the right, uh, this is kind of a graph of exoplanet populations that we found of different kinds, and we can see that they're clustered around certain specific kinds of planets, which tells us something about the universe. Also, you'll see that there's a small area in the bottom right labeled frontier. Those are the planets that we haven't really been able to detect so far with our tools because, as you can see, they're very far away from their star and also they're very small. So there's also a certain amount of selection bias in these planets that we found, and we'll talk about this in a second. But most importantly, the most famous reason for trying to find exoplanets is for trying to find life on other planets, right? This is kind of the reason that a lot of astronomers cite that this is that exoplanets are kind of our prime candidates for life outside Earth. And yeah, so when we are looking for exoplanets, detecting them is kind of only the first step. There's a lot more that we want to do than just detect them. We want to be able to try and characterize them much better than this, right? So we want to figure out their orbit, which is stuff like their eccentricity, inclination, etc. We want to figure out their density, mass. We can do spectroscopy to figure out their composition. And we do all of this partially to figure out whether or not these planets would be habitable and whether or not they can host life. So multiple methods will usually work together to give us a lot of different information about any particular planet. Uh, yeah. So how do you find a planet that you can't see? If you look at the image on the right, a lot of the times we have these, when if you look at, let's say, just the spectrum of visible light, you'll see this image of a star, and the star's own light will obscure the region around the star itself. So you can't usually see fine details like the planets orbiting the star, right? And our telescopes don't have sufficient resolution to make those out anyways. So in most systems, the star will just dominate this image. So we have to look for sort of side effects of the side effects that the planets would produce on the star. So they might make the star wobble. There might be some periodic event that they disrupt, things like that, to figure out what these planets are and to figure out what their properties are, basically. So let's talk about the first confirmed exoplanets. The first exoplanet that we found in 1992, at least the first confirmed one, was not around a sun-like star, which is where we find the majority of exoplanets today. It was around a pulsar, which is a rapidly rotating neutron star. And we confirmed this through a special method called pulsar timing variations, which we'll cover later on today. Uh, so basically, we found that the timings at which the pulses were arriving was slightly off, so we detected this planet. Interestingly, we now know that these kinds of planets are very, very rare. Only around 8 out of the over 6,000 planets that we know today have been discovered using this method because pulsars will very rarely have planets. And in fact, even pulsars are very rare. Uh, so that leads us to where we, in fact, do find exoplanets. If you look on the right, this is the HR diagram. This is pretty famous. On the top, you can see temperature. That's the surface temperature of the star. And on the left is luminosity. And we find that stars tend to exist only in certain regions of this graph. So if you look at the main diagonal, there's a very thick cluster of stars that's known as the main sequence. And there's a few other offshoots. Most of the stars that we discover exoplanets around are of what we call F, G, and K type, which is sort of close to the center of this graph, like close to a luminosity of 1 and around 5,000 Kelvin. So they're stars that are very similar to our own sun. And the reasons for this is just that these stars are pretty stable and they live long enough to make planet detection easier. So usually we find a lot of planets around these stars. But the fact that they're similar to the sun doesn't mean that the actual stellar systems are similar to our solar system, right? For example, one of the first exoplanets we discovered after we discovered the first one that I talked about previously was around a star very similar to our sun, which was a massive gas giant that was orbiting very close to its star. Its orbital period was only like 4 days. And this was a type of planet that we now know as hot Jupiters, which had previously only been theorized. So this discovery at the time was considered very surprising because we only had our own solar system to go off of course. Just as a side note, another interesting thing is that in our solar system, most of the planets have nearly circular orbits, right? Like the only one with any significant eccentricity is Mercury. But we found that in a lot of these other stellar systems, exoplanets have very eccentric orbits. So the only one, as I say, Mercury is the only one which has an eccentricity, I think, around 0.2. Over 50% of the exoplanets that we found have an orbital eccentricity of over 0.2. So we're finding that our solar system isn't necessarily a good model for for stellar systems across the universe. So that brings us to selection bias. So most of the planets that we find are going to be planets that produce strong signals that the methods and techniques that we use are very sensitive to. So for example, planets that are very close to their star and very large are going to be easier for us to find because they have like a significant impact on the trajectory of their star in the sky. uh, Sort of young and hot and large planets are easy for us to find, especially if they're like reasonably far away from their star, because sometimes we can directly image these planets, so we can see the light being emitted by these planets. Certain techniques can detect very faint planets, but for example, microlensing, but those events aren't repeatable. So very often we can't reproduce those signals. But selection bias uh, basically tells us that all of the planets that we found aren't necessarily going to be representative of all the planets that there are. This is just what our techniques are sensitive to. Again, like there was in the graph that I showed previously, there's the region in the bottom right marked frontier. These are planets that we can't detect because they're very far away from their stars and they're very small, too small for our methods to detect. So you have to keep in mind that there's some amount of selection bias in our data, and we aren't necessarily uh, seeing all the planets that there are. So there are 7 major ways to detect exoplanets, which we'll talk about today. These are pulsar timing, direct imaging, microlensing, astrometry, transits, radial velocity, and orbital brightness. Uh, Very often we'll use multiple methods to confirm the existence of exoplanets, for one thing, and also to try and detect different properties of the exoplanets like density, composition, etc. So, and especially, for example, we'll often use radial velocity to confirm potential candidates. If you look at the graph on the right, you'll see that, I don't know if you can see what's written, but I'll explain it. This is the graph of exoplanet discoveries over time, and the different colors signify the different methods. So, as you can see, especially as we come more and more into the 21st century, the purple bars are kind of dominating. That's detection of exoplanets via the transit method, which is very common. The green, which you can also somewhat see, is by radial velocity. And a lot of the other methods are less common, but they're still useful in sometimes discovering exoplanets and sometimes finding out more about their properties, right? Also, you might be curious why there's such a large peak in 2014 and 2016. That's because NASA released a lot of data, a lot of astronomical data around those years, which was analyzed, and so we discovered a lot of exoplanets in that time. Okay, so the first method that we'll cover is pulsar timing variations or timing variations in general. So there are certain systems where uh, they have some sort of periodic event that occurs in a fixed time period. So one example of this is pulsars. Uh, which are basically these sort of rapidly rotating stars, which emit EM radiation from sort of their poles. So if you look at the image on the right, you can see that there's this one star that's flashing, right? There's a sort of bright flash and then a dim flash. That star is a pulsar. So every time the every time we come face to face with the electromagnetic radiation that it's emitting, we see this flash. So, uh, wait, let me show you this. If you look on the right, this is sort of what a pulsar looks like. So imagine that you are an observer that is, and you're observing this head on. Then at twice the rotation frequency of the pulsar, you're going to see this flash of light, right? Now, as it happens, it's very unlikely that you're going to be observing it exactly head on. So there's going to be some angle. So that means one of the flashes is going to be slightly brighter than the other flash. That's what you're basically seeing here, where there's a bright and then there's a dim flash. So, and the type of pulsars that we use in our methods to find exoplanets are known as millisecond pulsars, which are these pulsars that have a time period on the order of milliseconds, and they can be timed with extreme precision. It's like a common statistic that they're almost as accurate as atomic clocks. And so if there is a planet orbiting about this pulsar, it's also going to make the pulsar orbit its own center, right? This is a well-known fact. Even in the solar system, the sun, for example, doesn't actually stay stationary, right? It orbits the center of mass of the combined system. So similarly, the planet will make the pulsar slightly wobble, which means that uh, at different times the pulse is going to be slightly further away from the Earth and slightly closer. So we're going to see some difference in the exact timings at which those pulses arrive, and we can use these differences to figure out things like the mass of the planet that's orbiting the pulsar, and again, just to detect the planet. So equation governing these residuals. If you let's pretend that there is no planet, then you're gonna see these pulses at some regular time t, and that you can like make a sort of graph of the brightness that you're seeing from the pulsar, right? Now, because of the planet, this these that graph is going to change slightly because this pulsar is going to be slightly further away and slightly closer at different times. And if you subtract this, if you try to look at the information that's basically observed minus theoretical, this is known as the timing residual. And the formula for the timing residual is, it's given on the screen. It's very simple. It's basically just uh, us calculating what the extra time is that the information takes to arrive, because the star is sort of as far away from us as it gets, right, on the other side of its orbit. And this is multiplied by a factor of sine I. I here is the inclination of the planet, so of the orbit of the planet. So it's not necessary that it's orbiting us face on, right? Like the actual system might be tilted somewhat, and so sine I is just to account for that tilt. I mean, the formula isn't really that important, but yeah, so this is basically the formula. With this formula, you can see that we can work out what everything else is, and so this will give us the mass of the planet times sine I, basically, right? Uh, this is what the actual real data looks like if you look on the right. And you'll see that it isn't very clean. You don't see any clean periodic signal. By the way, the x-axis is in years. So you don't see any clean periodic signal. This is because even apart from the planet, there's a lot of like fluctuations in the data that we receive from these pulses. One of the fluctuations is just that over time pulsars spin down, so they slow down. And so this signal won't be precisely periodic. There are also going to be effects, obviously, because of the Earth's motion and the proper motion of the pulsar in the sky. So we have to account for parallax and things like that. And there's also what astronomers refer to as glitches in the motion of these pulsars, where there's sometimes uh, reasonably predictable fluctuations in the data. So once we account for these effects, we're going to be left with one of two things. If there is no planet orbiting the pulsar, we should see essentially a flat line, which just means that our observed data is the same as our theoretically predicted data. If there is a planet orbiting the pulsar, then we are going to see some kind of periodic signal that should tell us a little bit about the planet. And this is an example of what that periodic signal could look like. Again, the x-axis this time is the actual year from which the data is captured. So if you look at this, this is a periodic signal, right? So we can try and fit different models of what we imagine the system might be onto this. So, so this is done completely computationally, by the way. So Basically, we might try and fit a two-planet model onto this, and then we vary the parameters like the mass of the planets and their semi-major axes and things like that until we find something that's numerically a very close fit. And so basically, just using computers, you do this until you find whatever the best fitting model and parameters for the system are, and then we have like a reasonably good guess that this is probably what that system looks like. Yeah. So there's a number of pros and cons for this method. This is a very, very sensitive method because, again, pulsar timings are very reliable. So this can help us identify planets down to less than 10% the mass of the Earth, which is much lower than most of the other methods can manage. But it has two main drawbacks. The first is that pulsars are very rare. So there's very few pulsars for which we can take this data. And the second is that even the ones which we do have, very few of them probably have planets around them because they're, the formation of pulsars is like a very high energy event, and usually this is not conducive to planets orbiting them. So some of these pulsars that we have detected have very exotic planets orbiting them. Like there's one that has a planet that's made entirely of diamond, things like that. Also, there is lesser scientific interest in these planets because there's going to be a lot of radiation striking them, so it's very unlikely that we're going to find life, which was, again, one of the main objectives of exoplanet detection. Yep. So this move on to the next method. The next method is just direct imaging, which is to try and detect the planet as a faint point source near the host star. As I said before, direct imaging is almost always impossible. It's very difficult because the star's own light will obscure things around it. So it's very, very hard for us to actually be able to resolve the planet from the star. But in certain specific situations, this is possible, especially when the planet is able to emit its own infrared radiation of some kind. So if it's heated up, things like that. And usually, when we say direct imaging, we don't actually mean being able to see an image of the surface of the planet. We just mean that we can resolve the planet as a point source of some sort of EM radiation, right? So conceptually, this is very simple, but as an engineering and technical problem, this is very hard because our telescopes usually don't have this resolution. This is just to show you, roughly speaking, why this is so difficult. Like the image on the right shows you the sort of images that we will get from telescopes. You can see that the stars more or less obscure what's around them, at least in a small radius, right? And on the left, there's a formula. This is the flux that we get from the planet divided by the flux that we get from the star. And so, roughly speaking, this gives us an idea of how much information we are getting from the planet. So you can see that, first of all, it's multiplied by a factor of RP by A whole squared, which is RP is here is the radius of the planet, A is the semi-major axis of its orbit. So this is essentially telling us, uh, this is kind of telling us how large the planet is compared to how close it is to a sun. So basically, if I have a small planet that is very close to its star, then this ratio is going to be very low. So its square is going to be even lower. And if I have a large planet that's relatively far away from its star, then ratio is going to be high enough that I might have a chance of getting some decent flux from it. The other two terms, PF lambda is just geometric albedo, which is a measure of how much radiation, just geometrically, if I were to shine some sort of light on the planet, how much radiation it would reflect towards me as an observer. So, for example, for a perfect sphere, this number is around 2 by 3. Not for a perfect sphere, for a sphere with the property that it reflects an equal amount of light from all directions. And the other function here, GF alpha, is just a function that depends on the current phase in the orbit of the planet. So basically, the specific actual value for the flux depends on a number of factors, but the important takeaway here is the RP by A ratio. So planets that are very close to their stars, it's going to be much harder for you to make them out. So yeah, the effects that you need to account for when you're doing this, there's a number of effects that matter. The first is obviously what we've discussed, that the flux ratio is massively against you. So you need very specialized, uh, very specialized devices and techniques. The second is that effects like diffraction are going to create rings. So that's going to further distort the area around the star in your image. So it's going to be much harder for you to make out the planet. Uh, and if you look at the image on the right, on the first image, A, you can see that even if you get this perfect wavefront coming from the star, there's different, pockets of hot and cold air in the atmosphere. It's not homogeneous. The atmosphere is not homogeneous. So by the time the wavefront gets to the ground, it's going to be pretty significantly distorted. And this distortion will make it even harder for you to find the planet where you expect that there is a planet. So one way to get around this, to get around atmospheric distortion is, of course, to use space-based telescopes. But the other issue is that these planets are small enough that even very small optical imperfections in our instruments might actually just look like planets to us. So if you look, there's this photo there of what's called speckle noise. That's because of optical imperfections. And so even these very small imperfections can cause issues for us. So you need very perfect instruments. Uh, So obviously large apertures will help us separate close objects because large apertures will increase the angular resolution that we are actually able to see. Uh, if you look on the right, that's the um, James Webb Space Telescope, which has very large aperture, and it was used to directly image at least some relatively close by exoplanets to get some of the first such images. Uh, yeah, and if you look also, incidentally, the resolution theta min is directly proportional to lambda. So for larger wavelengths, we're going to be able to see uh, essentially not quite as much. So we want over here, we would ideally want this resolution to be very high. So we want like large visible wavelengths, right? So the best candidates for this are planets that emit some sort of infrared radiation, which has a large wavelength. So the targets basically. So to date, we have managed to get the first few images of these exoplanets, which again satisfy those conditions I talked about earlier, where these are large planets far away from their stars, and none of them really resemble the solar system in any meaningful way. The detection of planets that looks like Earth is still out of the reach of any of our current telescopes and imaging facilities. And again, we can just use it to detect those specific types of planets that we talked about earlier. Oh, this is an interesting image. If you look on the right, this is we've imaged an actual stellar system, and you can sort of see there's three planets. There's the central star, which has been blocked out to prevent its light from hindering us too much. And then there's those three planets on the outside, and you can sort of almost follow their trajectories as they go along. This is one of the um, oldest oldest of these exoplanet images that we have. I think this was compiled using 12 or 16 different images, and then they just interpolated between those images. Anyway, so why do we want this? So the first reason is for what you can see over here, imaging over a long period of time. So this was over a period of a few years, can help us trace the orbits of these planets. If we are able to precisely image them, the brightness can help us estimate things like the surface temperature of the planet and its mass. And of course, if we can image them very precisely, then spectroscopic analysis can tell us about the composition. So we can find out, for example, the composition of the atmosphere of the planet, things like that. Okay. Next method that we'll talk about is gravitational lensing, which is where an object, like a star in the foreground, passes nearly in front of a background star with respect to us, which causes it, because of general relativity, to bend the light coming from the source. And so if there is a planet that is going around this lens star, then we'll be able to detect this as a slight anomaly in what we would expect to see otherwise. Uh, yeah, so there's an animation here. This is kind of what it looks like. If you look at the planet passing in front of the actual observer, and then this kind of, because of general relativity, this will sort of split it, and we'll see two sort of indistinct images. Now, in real life, it's usually not going to be, especially for planets, you don't see two distinct images, but it does measurably change what the brightness looks like, and like what the brightness looks like over time. So we can use this change to try and detect things. Yeah, so again, if we let's talk about the different types of gravitational lensing. There's three main types. The first is strong lensing, where it's being lensed by a very large mass, like a galaxy or a galactic cluster. And so you're going to see some significant distortion because the mass is very large. And if the geometry is favorable, so if the observer, the lens and the source are nearly in a straight line, then the observer will very cleanly see two or more separate images of the source. The second is weak lensing, where the lens is again a large mass, but the geometry is not so good. So the image will be slightly distorted. And the third, which we care about, is micro lensing, where the lens is some very small mass, like a star or even in some cases a planet. In such cases, because the mass is not so large, we can't actually resolve the multiple images that are formed. But because light from the source is sort of being bent inwards towards the observer, the image of the source appears to brighten slightly during the duration of this alignment. So we can see that it brightens like this. And if there is a planet going around the star, then the graph will have like a slight anomaly which we can detect. So this is just the formula for how the lens will bend light. It's proportional, as you can see, to the square root of the mass of the lens, which is the main factor that we care about here. Yeah, so if you look at the graph, the actual lens will create like this smooth kind of brightening. And in the absence of the planet, it would have just gone down symmetrically. But because of the planet, it's slightly perturbed. And because we can detect this, we can see that the brightness is rising over time, then falling, and then rising again. We can measure the magnitude of this effect to estimate the mass of the planet and to detect that it's there. And what are the strengths of this? The strengths of this are that this is very, very sensitive, right? Like as we saw earlier, it's proportional to the square root of the mass. So uh, even fairly low masses have like pretty similar effects to higher masses, right? And so what this means is that it's going to be sensitive to relatively faint systems on the front. We've been able to use this method to even spot what are known as rogue planets, which aren't actually going around any star. They're just sort of floating between stellar systems. They've been ejected from some star system and they're just floating. And through this method, you can also spot very low mass planets, which are down to the mass of the Earth, because even with this very low mass planet going around the star, it's going to have an observable effect on the brightness, because again, even low masses actually have a significant effect in lensing. But there's a lot of limitations to this. As you can see, very few planets are actually discovered using this method because this is only like a one-time alignment thing. It's like a one-time event. Once this alignment passes, the event is gone. So you can't actually repeat this to get repeat observations. For Earth-like planets, this event is only 4 or 5 hours. So you have to take measurements quickly, and you know that you can't repeat it. So you have to follow up quickly. And what this means is that if you confirm the existence of this planet, for one thing, it has to be through other methods. And also orbital parameters within those 4 or 5 hours are much harder to refine than in repeated transits or through the relative velocity method that we'll discuss later, because all of that is usually done computationally, and it's much better if I have a lot of data. And I'm not going to have a lot of data from this one-time event. Yep. Okay. So we'll move on to the fourth method, which is astrometry, which involves just directly observing the motion of the star about its barycenter in the celestial plane. Again, like we discussed earlier, for pulsar timings, the presence of a planet around the star is going to make it slightly wobble. And the star and the planet will both orbit some common center of mass. So we can try and measure the star doing this motion directly in the sky. And what this should look like is a sort of small ellipse in the sky or small wobble, right? The animation on the right is slightly exaggerated. So in reality, it's going to be, even this is slightly exaggerated, but it looks something like this, where you'll see a small, this actual star is like slightly wobbling in the sky. This was, in fact, the very first method that astronomers tried to use to detect exoplanets, because they said that if the exoplanets exist, then we should expect to see these stars wobbling in this manner. But at the time, the tools that they possessed were not sophisticated enough. So the resolution was too large, which meant that obviously we couldn't actually measure the wobble. So it wasn't sufficient for us to detect these exoplanets. The amplitude of the wobble is given by this equation. And so again, what you should see is that it's proportional to the planet to star mass ratio. So large planets will have larger effects on the star, obviously, and it's proportional to to the relative distance of the planets. So planets that are close by to their star, and obviously which are close by to us, we'll see a large wobble. And if the planet itself is far away from its star, or the whole system is far away from us as the observer, then we're going to see a much smaller magnitude of wobble. Uh, when we measure these positions using our telescopes, there's again a lot of the same problems that we need to account for. We need to account for the proper motion of the actual star. We need to account for parallax because of the Earth's motion. And again, we need to account for the scattering by the atmosphere. So different wavelengths get scattered differently, which means that if we gather data across different wavelengths, we're going to see the star in different positions, which will sort of throw some noise into our data, things like that. After we model all this, if we still see some sort of small periodic motion of the star, then this suggests that there is some planet in the system that we can again use other methods to find more about. The basic issue with this is just again the same resolution issue. We need to measure these angles at micro arc seconds, so it's very difficult to get precise measurements. The advantages that this offers is that for certain sorts of systems, again, if they're nearby to us, we'll see a large magnitude. And for very large planets, we're going to see a sufficiently large magnitude that we can easily detect it. And also, so like we discussed earlier, some methods like the pulsar timing method or radial velocity give us different answers depending on inclination. Like we discussed, the pulsar timing method only gives us the mass of the planet times sine of the inclination. If we use that method in conjunction with this, we can sometimes solve for the actual mass of the planet because we have two different data points that we can combine to solve the simultaneous equation. Yeah. Any questions so far? Okay. I'm assuming no questions. So, Paras.
Yeah, I will present.
Yeah. Okay.
Okay, is my screen visible?
Yep.
Okay, I'll check. Okay, so we'll start with the next method, which is transit photometry. Transit photometry is the basically it is the easiest method to picture. Just imagine that there's a star and we are looking at the star and measuring its brightness again and again. If a planet passes in front of the star from our point of view, it blocks a small part of the star's light. So the star would look slightly dimmer for a short time. If the same dip keeps on happening again and again after a fixed time interval, we suspect that a planet is orbiting the star. And yeah, the power of this method is basically scaling. So there are several missions like Kepler or TESS, and what these do is they do not necessarily watch only a single star. They can monitor thousands or even millions of stars and search for repeated brightness dips automatically. So yeah, the depth of the dip tells us the size of the planet. The reason is just area. A bigger planet would cover more of the star, and a smaller would cover less of the star. So the drop will be smaller over there. The slide shows you the formula for measuring the dip. You do not need to derive it, just remember it that obviously deeper planet would mean so larger planet would mean that it gives a deeper dip, and like a Jupiter-sized planet crossing a sun-like star would block about 1% of the light coming from the sun, and an Earth-like planet crossing the sun would block about only 1 in 10,000 part of the brightness of the sun. So such planet would be harder to detect for us. Why do most planets do not transit? So yeah, here's the catch that most planets do not transit from our viewpoint. A transit needs some lucky geometry. The orbit must be almost edge on so that the planet crosses the face of the star as seen from the Earth. If the orbit is even slightly tilted, the planet may pass from above or below the star as shown in this animation. And we do not see a dip, or we even if we see, it's not a noticeable dip for us. So yeah, transit surveys are naturally biased towards shorter period planets and which are very close to the stars. A real transit is not just one brightness value going down, it has phases. So yeah, first the star is at normal brightness, then ingress starts. Ingress is basically the planet starts to enter the star's disk, and then the brightness slowly falls. During the main transit, the planet is fully in front of the star, and the light curve reaches its lowest part. In this period, it is normally constant as the amount of light blocked by the planet after entering the star's disk is constant. After which egress starts, and egress is basically the planet leaves the disk and the brightness returns to the normal level. This depth gives us the ratio of the radius of the planet to the radius of the star, and the duration tells us about the path across the star. The duration would also give us sometimes the orbit's period or the planet's whatever time the planet takes to revolve around the star. So in simple diagrams, a star looks like a flat yellow circle, but real stars are not like that. They are glowing gases of spheres, right? So what usually happens in real stars is the center of the disk is usually brighter than the edge. So we exactly do not get a constant graph over there. The graph would fluctuate a bit, and this effect is called limb darkening because the edges are basically darker than the center. It is not having a uniform illumination over its area. This is why real transit curves are kind of rounded instead of being perfect rectangles as this one. Astronomers include this effect in their models so that radius and orbital geometry are measured correctly. Not every dip is a planet. A dip in brightness is not automatically a planet. An eclipsing binary in which two stars passing in front of each other can also create repeated dips. A faint background binary can blend into the same telescope pixel and imitate a planet-like signal. And yeah, there is a chance that even because star spots also rotate in and out of view and change the brightness of the star, so we can also see dips in that case. If star spots, or in our sun's case, we call them as sunspots, they change the brightness and the flux emitted by the star. Before moving, I'd like to add that to confirm the presence of a planet, we need to, whether it is repetitive or not, and we also have to measure the stars, like whatever the information we have about the star of its temperature and radius with actual measurements if it actually had a planet. Transits can also probe atmospheres. So transits become even more powerful when we add spectroscopy. During a transit, a tiny fraction of the starlight passes through the planet's atmosphere before reaching us. So molecules in that planet's atmosphere, they can absorb specific wavelengths, and by comparing the star spectrum during the transit with its spectrum outside the transit, astronomers can search for gases such as water vapor, carbon dioxide, methane, sodium, and others. The James Webb Space Telescope made this field especially exciting because, for example, James Webb Telescope produced a very clear detection of carbon dioxide in the atmosphere of an exoplanet WSP 39P. So transits can tell us more than size; it can also tell us about the contents of a planet's atmosphere. All right, moving on to the next method, which is radial velocity. Now, suppose a planet never crosses the star. We can still detect it by watching the star itself and not the planet this time. What we do is we watch the stars over here. Radial velocity uses the Doppler effect. Now, you may have been familiar with this term, the Doppler effect, which is basically changing of frequencies as a source, like if a source is coming towards you or going away from you at a certain velocity. Similarly, light also shows Doppler effect as it is also a wave. When a star moves slightly towards us, its spectral lines shift a little towards blue, and when it moves away, shifts a bit towards red. Now, if this red-blue pattern keeps on repeating, It suggests that something is pulling the star back and forth. This something can be an orbiting planet. So yeah, the star wobbles. Now it feels natural to say that planets orbit stars, but the stars they do not stay perfectly still. The star it's also revolves around the common center of mass of the star and the planet, which is called as the barycenter. Now, because the star is much more massive and the object is tiny, but it's not zero. So it will cause some motion for the star. If the planet is very massive, it will pull harder, and so the star wobbles more. A close-in planet completes orbit quickly, so the signal repeats quickly. Whereas if a planet is located far away, the signal would take time to repeat itself. Radial velocity works best when this wobble is along a line of sight. If the system is face on, most of the motion is sideways. So Doppler signals become very small. So yeah, even again, the face on system is not good for us because the Doppler signal would be very small. When we plot radial velocity over time, we get an RV curve. The repeating time of the curve gives us the planet's orbital period. And the height of the curve would give us the velocity amplitude and tells us how strong the pull is. And using this data, we can also get information about the mass of the planet and the star system. And yeah, this shape is also very useful as a perfectly sinusoidal graph would indicate that the orbit of the planet is circular around the star. If it is kind of distorted, then we can suggest that it is an eccentric orbit, and we further also have methods to calculate the eccentricity of the orbits. Okay, now the important limitation is basically inclination. A spectrograph only measures motion along our line of sight. If orbit is edge on, we almost see the full toward and away motion. So if the mass is if the mass estimate is close to the true mass, and if the orbit is tilted, we see only a part of the motion. If it is face on, we almost see no radial velocity signal at all. This is why radial velocity usually gives a minimum mass written as mp into sine I. I is basically the inclination angle, and a small signal means that it is a smaller planet or a larger planet viewed at an unfavorable angle. So yeah, this is why transits and radial velocity are such a powerful pair. And normally, radial velocity alone cannot give us the true mass indication unless inclination is known very well. Radial velocity sounds clean, but stars are really messy. Their surface boils to do convention. This is why the stars also vibrate, and there's also some magnetic activity due to the stars. Like there are several spots, star spots, such as I just gave example, are sunspot. They have certain magnetic activities around them also, and as the star rotates, these features change the shape of the spectral lines, and they can imitate a planet's signal. So yeah, we due to this noise also, it's sometimes suspected that exactly it is not a planet. It can be due to the magnetic activity of the star itself. So yeah, astronomers use reference sources such as iodine cells, thorium argon lamps, or laser frequency combs, and check the line shapes to see whether the whole line is really shifting or whether the activity is only distorting the line. Yeah, RV loves massive and closing planets. Radial velocity naturally favors massive planets because it would give significant changes in the radial velocity. And massive planets, they also massive planets pull the stars with a much greater force, which is significant. And closing because the more closer the planet is towards the star, the more the star will wobble. That's why. There's a famous example, which is the 51 Pegasi B, discovered in 1995. It was the first planet found around a sun-like star, okay? And it orbits only around about 4 days. This is a graph of the 51 Pegasi star. This shocked astronomers because Jupiter-like planets were expected to live far from the stars. But as you can see over here, this star, 51 Pegasi b, it was almost Jupiter-like star, and it had a time period of around 4.231 days only. So such a massive planet was so close to the star, a sun-like star, especially. If you want to learn more about radial velocity, you are welcome to scan this QR code and further explore yourself. So now we get to the real payoff. Transit photometry gives radius, radial velocity gives mass, or at least the minimum possible mass. But if the planet transits, we know the orbit is almost edge on. So the inclination problem is mostly solved because of the inclination problem being solved, we can say that the mass of the planet, whatever we detected, MP sine inclination is almost equal to mass of the planet, whatever we assumed it to be. Now, no method seeks the whole truth alone. No single method gives us the whole planet. Each method sees one part of the truth. Like transit gives us radius and period but needs alignment. Radial velocity gives us mass information but struggles with inclination. And imaging gives us actual planets, light and spectra, but is only favorable for light and separated planets. And astrometry can well help us measure true mass and orbital geometry, but it needs extremely precise and long-term measurements. And for microlensing, as they kind of can find planets far away, but uh, usually from one-time events only, not multiple times. So yeah, this is also an important term to be considered that we need a periodic data. We do not need continuous data. The more periodically changing data we get, the more and more we can confirm the presence of a planet in the orbit. The strongest exoplanet science comes from combining methods. So we cannot rely on one method alone. We normally use two, three, or even more methods for a single exoplanet, which finally gives us the confirmation of the presence of a planet. Each method has a favorite planet. Now, yeah, as you can see, transit surveys favor close-in edge-on systems. Radial velocity favors massive planets, especially close-in ones. Direct imaging favors young, hot, and wide orbit giants. Microlensing can favor distant planets and wide planets, and yeah, rest you can see over here. And yeah, also you can see over here that transit has led to around 4,000 discoveries and radial velocity has led to around 1,050 discoveries, which is why they are such popular methods and are commonly used because the probability of finding a planet using these methods and also confirming the existence of an exoplanet is easier through these methods. Okay. Now, mass and radius tells us what a planet is exactly be made up of. Density is useful because it connects measurements to the composition. If a planet is high density, it may be rocky and iron rich. If it is very low density, it probably has large gas envelope. But density is not a complete answer. A rocky planet with a thick atmosphere and a water-rich planet can sometimes look similar in mass radius space. Like our Earth, it is kind of a water-rich planet, as you see. It We still look at it as a rocky planet, but no, it has a liquid surface also. Majority of its surface is liquid. Earth is considered as a rocky planet, by the way, but it just happens that liquid water exists on our planet. That is why we can say that it comes in the habitable zone. That is why liquid water is present on it. If it's much, much closer, then liquid water would evaporate into vapors. If it's much, much farther, then it would be present in the form of ice, which both of them gives us kind of a rocky structure, like completely rocky. Now, talking about habitability, habitability is where we must be careful. Habitable zone only tells us the distance where liquid water can exist on the surface. But it does not give us information about atmosphere and stuff on the planet. It does not directly mean that the planet has life. The planet must be right size to hold an atmosphere without like becoming a mini Neptune, which is basically it should be able to hold on to its atmosphere. Its atmosphere should not escape in this space. Then the star must not strip the atmosphere away with strong radiation and flares. And yeah, basically, it should withstand strong radiations and flares also to sustain life. A magnetic field, geology, pressure, greenhouse gases, clouds, and all the surface conditions matter when we are talking about life. Liquid water is the first and basic condition. So, habitable zone gives us a target list. It does not exactly answer that a planet is habitable or not. Okay, any questions till now?
There was a question on the WhatsApp group.
Okay, okay, I'll see. Yeah, a gas cloud would normally see if it's a solid planet, then it would give periodic ups and downs. A gas for a gas cloud, what normally would happen is either it would surround the star, or it would form a ring-like structure, you can say, due to angular momentum. But yeah, a gas cloud would normally not be uh, like the question asked over here would be true if it was something else than a planet. Like you can say for another stars, as I mentioned, you cannot confirm. It can be a binary also, which gives regular ups and downs. But no, for gas clouds, this is not a problem. Gas clouds eventually settle up and orbit in a circular space, which would not give dips. And gas clouds also don't block that much part of a sun's of a star's basically light as a planet would. Okay, I'll answer the next question. Okay, wait. So you're talking about the BLS algorithm over here, and what's asked is, oh, we haven't exactly evolved into such models right now. But yeah, there are certain systems which are trying on AI and machine learning models. I'll talk about them a bit further. And yeah, after talking, they are trying to change everything into machine learning models to study it better, study such methods, especially transit and RV better. But the shift right now is not like seen. But what I have heard is they are trying to slowly shift towards machine learning models. I'll still see and get back if there are any such models present and give you an example. The thing is, it's not that reliable right now. Okay. Yeah. Even I am not having that much information about AI based programs right now. All I have is the like basic theory which is present. I'll surely research and get back if there's any such models present. Yeah. Any other doubts? Okay, we'll move on. So the future of the exoplanets is about precision and scale. Precision means measuring smaller signals, smaller dips, smaller wobbles, and fainter spectra. And scale is basically doing this for many, many more stars. Now, space telescopes avoid Earth's atmosphere and can observe in important wavelength ranges. Ground-based telescopes will use huge mirrors and adaptive optics to sharpen images, and detectors are used to there are improvements in certain detectors to reduce noise. And yeah, global telescope networks help us catch events that can happen at inconvenient times, such as there is an example as ESA's Plato mission planned for January 2027. It is designed to search for terrestrial planets around bright stars using 26 cameras. And NASA's Roman Space Telescope will also transform microlensing into wide field surveys. So there are further plans being made. And yeah, now as I'm talking about, modern surveys produce far more data than humans can inspect by eye. This is where machine learning helps. Machine learning can scan light curves, rank possible transit signals, reject common false positives, and basically help us model noise. It does not replace astronomers. It basically creates a short list right now. A famous example of such system is Kepler 90I, which is found using a neural network trained to identify weak transit signals in Kepler data. The system is become known as like an eight planet systems, like our solar system and planet count. And yeah, the more important idea over here, basically what I'm talking about is AI is just for pattern recognition and careful validation. It is not exactly going to replace whatever manual work we are doing. It is just going to be used as an aid. Now, because even machine learning models need lots and lots of data to be trained so that they can detect such observations. And even humans, when humans used to manually detect such observations, they used to intentionally detect there is some new pattern over here. This might be an exoplanet, and this is how it helped. Machine learning models, they work on a fixed algorithm, so they'll not help us discover if there's any obscene, or you can say there's any a pattern which was not recognized earlier and it's of some new kind. Yeah. From raw light count to candidate list. So basically a typical pipeline has several steps. First, you have to clean the data by removing instrument trends, cosmic rays, and bad points, so which basically clean the data, they call it. Then, second, you have to search for repeated dips using transit search algorithms. So you have to search for periodic dips because periodic dips normally indicate that something is revolving around the star. And then third, you have to measure features such as depth, duration, SNR, and the shape of ingress and egress. Then you can use a machine learning model to separate planets from false positives. And yeah, finally, you can take a follow-up using some ground-based photometry, radial velocity, or high-resolution imaging, or even spectroscopy. So the pipeline does not end with the computer output. It usually ends when the signal survives physical tests also. Basically, human tests, what I just said. Now, talking about the exoplanets, atmospheres, and biosignatures. So, yeah, the next frontier is not just about finding planets, it is asking what kind of planets they are. Transmission spectroscopy can reveal gases like water vapor, carbon dioxide, methane, clouds, etc. Direct spectroscopy can study young giant planets by measuring their own light, whatever own light they are emitting. And future missions may attempt reflected light spectra of smaller, cooler planets around nearby stars. So, yeah, whatever light is reflected from the surface of the planet due to other stars, that can be calculated, but it is not available through the current technology for us. We have some future plans for it. And yeah, oxygen alone is also not a proof of life. And even methane alone is not. Even oxygen and methane together required some context. We need to understand the star, planet size, geology, and radiation environment. Then we can say that uh, some life can be present. And here's a chart. This basically helps us to separate biotic from abiotic processes. oxygen can be detected in this third planet, for example, due to whatever we have. Basically, the breakdown of O4 molecules due to photons of the sunlight present, it can create O2. So here O2 is getting generated by, we can say, due to the sunlight, right? And not due to biological processes. So we refer it as abiotic processes, basically. Then similarly, these gases emitted in yellow, they can uh, also produce O2 under certain uh, process due to certain radiations. So we also cannot exactly determine that if O2 is being produced, is it being produced by biotic or abiotic processes? We have to find that out also. So for that, we look for other components of the atmosphere that if this particular molecule is photoradiated, can it produce oxygen? Now, yeah, which method would you choose? So you have to now see that how is the star behaving, how is the star's nature, and then you can basically decide that, yeah, this method will be good, that method will be good. The goal is basically matching the observable to the physical cause. Brightness dip means geometry, spectral shift means motion, and one-time brightening means lensing. And a separated point of light means imaging. And here you can see how exoplanets are detected using different methods. Think about observable stuff first. Now, yeah, what is actually changing my data? If brightness dips periodically, think transit, but also remember that it needs alignment. If spectral lines oscillate, think radial velocity, but remember it gives minimum mass unless the inclination is known. So you have to think about all the possibilities and all the constraints also to actually see which all methods I can use and is the data that I'm getting factually correct or not. So yeah, for using any method, you should first see that what I'm observing, will it be good for this particular method? Then look at its weaknesses. That what weakness did this method have? I have to check for all. Okay, now let's have a recap of our today's session. So planets reveal them indirectly. Direct imaging is very, very rare, as you can see, because it is almost impossible for small planets. You won't be able to detect it using direct imaging. So indirect methods like we have seen transit and radial velocity, they are more useful in detecting exoplanets. Yeah. So basically, it's the star's gravity or the geometry creating shadows or relativity magnification due to relativistic effects. Basically, these are the things due to which we actually are able to detect exoplanets, not directly. And even if we get information about certain exoplanets, whatever images that you might see on Google and things, they are not the actual images. They are approximate images of the exoplanets, which are created using the contents that we got information about. One of the most important scientific lessons is selection bias. A survey does not show the universe perfectly. It shows what the survey is good at detecting. As we see, transits miss most non-aligned systems. So there will be several non-aligned systems which we have missed because transits cannot work in such, and even RV cannot work much better in such scenarios. So whatever we have found about exoplanets is just a fraction because if you see the probability, you will see that there can be much more planets which we have left because every planet cannot have edge on alignment with the star that we are observing. That's why. And yeah, confirmation needs consistency. Because the signals are indirect, confirmation requires a certain consistency. A real planet should produce a repeatable signal whenever repeatability is expected. It should survive all the checks against eclipsing binaries, star spots, background blends, and instrumental effects. Its mass, radius, density, and orbit should make physical sense together. And independent methods make the case stronger because they test different explanations. So yeah, good science is basically not just finding a pattern, it is to try to break your own explanation and see that does this pattern survive? Whatever I am observing, is it actually what's happening over there? So yeah, moreover, the exoplanet hunt is a measurement problem. Hunt for exoplanets is one of the most greatest measurement problems in astronomy. We measure brightness change as one small part in 10,000. And yeah, we measure stellar velocities of only around 3 meters per second. And for Earth-like planets around Sun-like stars, the signal is so weak and so small. We only measure tiny angular shifts and faint atmospheric fingerprints across light years. The universe keeps producing such signals all the time, but they are small, noisy, hidden inside much brighter light and whatever stuff we have. Okay. So yeah, that brings our today's session to an end. Thank you. And yeah, we'd like to take questions. I hope you found today's module interesting. Exoplanets are a very interesting topic, and the progress that humans have made that we can detect if there is a possibility of life in a planet far thousands and billions of light years away. And yeah, like then it is a planet revolving around such a star, and we can still are able to say that this particular planet can or cannot sustain life is a very incredible achievement for humankind. Also, as I would like to add that as you can see, Earth-like planets which revolve around sun-like stars are so difficult to detect using common methods like transit and radial velocity. So you can also imagine that if there's a guy sitting really far away in some other galaxy on some other planet and he's trying to detect our planet Earth, he would most likely get no trace of such planet, and instead he'll be able to detect some small information about Jupiter only in our solar system. So it's very difficult for people from far away to detect our Earth also. So similarly, it is also difficult for us to detect Earth-like planets far away. So there may be many more planets which can sustain life, but we are not able to detect them due to our technical limitations. Oh yeah,
There's okay.
yeah,
No, I
I
was
saw.
just telling you
Yeah,
there's a question.
I just saw. So yeah, there are several factors. I think I had mentioned there can be star spots also, and then there's limb darkening, which can like change or vary the depth. Most of the time, it's star spots only. Star spots are nothing but cool, dark regions on the stars, which are basically a bit. They basically emit less light or produce less flux than what the star is supposed to produce at such temperatures, and that is why it also creates a dip, which can be like which can be misinterpreted as an exoplanet, but the most common method to solve it is to check its periodicity. If it's not periodic, it is not an exoplanet basically. Planets have to be periodic. Star brightness may itself also fluctuate. It is possible, I think, if you have heard about variable stars. Have you heard about variable stars? Yeah. So in such cases, it is difficult, but what is done in such cases is because variables also have fixed change in size and hence they have a fixed change in the amount of flux they produce, right? So what we do is we map the flux curve, and then if there's any regular dimming, because variables they also have a fixed process only of changing their uh, uh, brightness and size, and they also have a fixed time period. So in such stars, it is also easy to measure because everything is periodic now. Even the changing of the sizes is periodic, and even the planet's rotation is periodic. So there will be a periodic dip, but it kind of becomes difficult to see because both of them are changing repeatedly. And because if the exoplanet is very, very small and it's creating very, very less change in the flux as compared to what the variable's size is doing, then it is difficult to detect such exoplanets. Yeah, mainly that only. Basically, exoplanets, their primary source of detection, or like the first thing they check is periodicity in exoplanets. Periodicity is the first thing to put them in confirmed and potential, like, yeah, potential, sorry, not confirmed, potential.
And also, for example, like radial velocity only gives us the lower limit on the mass of some potential exoplanet.
Hmm.
So if that limit falls within the range of mass for a planet, then we might call it a potential exoplanet. And then with some other method, we might get some kind of upper limit, and that'll confirm that it's a real exoplanet. Things like that.
Hmm. Most probably, if through transit and through radial velocity, both the informations they usually kind of, if they kind of match, then it is confirmed. The existence of a exoplanet is confirmed. Yeah. Exomoon, yeah, exomoon is further more difficult to. It's almost like I don't think there's any exomoon actually discovered as of now. It is possible if the planet is like it can be possible, but it's mostly hypothetical only. Like not hypothetical, sorry, difficult to do it right now. The exoplanet itself is so difficult to detect. The exomoons are further. It's yeah.
And I think with most of our
Uh,
methods, except maybe direct imaging, you can't really differentiate very well between exomoons and exoplanets.
yeah.
And even with that, our
If
resolving power is too low, so we can't tell anything right now.
If the exoplanet is like really, really hot, which produces a noticeable flux of its own, then maybe we can detect exomoons, but there's no such planet found till now because it needs a very, very high temperature, which is not practically possible. Yeah. All right, I think, yeah, everyone's done. If you have any more further doubts, you can ask us on the group or DM us. And yeah, with that, we'll be concluding today's session. Hope you had fun. All right. Bye. Have a great day.
Thank you. Bye bye.